Thank you, Patrick. Good afternoon. So I would like today to speak about the optical technologies behind the AR device, and to show you this is optical technology is really a key. You just see an excellent paper from Rgb Led about the optics. I think if you compare the optics and the electronics, optics couldn't follow Moore's law. There is some size issue, some efficiency. So here is the summary of my talk. I will start first with the ergonomic and photometric parameter for near to eye, mainly because all these systems should be placed in front of the eye. And then I will give an overview on the existing AR technologies. We compare them with their advantage and drawback. And then I give you my personal opinion and future trend in optical technology for AR. And then I also give some opinion on light feed technology. This slide explains first the display model basic ergonomy. By display model, we mean the display function. Sometimes we are talking about display engine. It means it's an assembly of the optics of the micro display, right? There is no computing there. So here you could see there is a micro display. I think there is pointer. Okay. Anyway, there's micro display which make the image, and you have a kind of lenses to magnify the image, and you have the eye on the left. So the main parameter for any near-to-eye display, you have two. The first one, what we call the eye relief, which is the distance between the last optics, it could be light guide or whatsoever, and the eye, the pupil eye. And the second is the eye box. So what is the eye box? Is the area where if you put your pupil, you could see the whole image. So the pupil, the human pupil, is about 4 millimeters, between 3 and 6, depending on the brightness. But you cannot afford to have a system with very small eye pupil. You have to have large in order to afford different interpupil distance, and also to have visual comfort in order, even when you move your eye, your pupil move. So these are the two parameters that should be there for any system. Here I give some value for the eye relief between 20 to 25 millimeters to accommodate the user to put their correction glasses. And for the eye box, you should have at least 10 to 7 millimeters. By vignetting mean, we should have all the field, all the image without any loss. The rest is you should have a transparent display, at least 30%. Some technology could afford up to 80%. And the weight of the whole system should be less than 30 grams, especially if you have binocular, to have the whole glasses less than 70 grams. And mandatory, you should have a solution to correct the vision of the population. More than 50% of the population are wearing glass. You cannot force people to have another correction than his own correction. So now the other requirement regarding the photometry, which means the brightness. So the brightness in this system, we are not talking about projector where the light flux is in lumen. Here we are talking about nits. It means we need to have the right value for brightness in order to use these devices outside and inside. Give a value. If you are outside, the brightness can go to up to 10,000. Actually, for car, the required value is even higher, 12,000. And for dark night, it could be very, very low. So how to get high brightness? Of course, you need a display with high efficiency that consumes less watt. Here I give a value. A good system should deliver you 10,000 nits for 1 electric watt. If you have less, it means you need larger battery and or less lifetime. You could also manage this by having light sensor in order to adjust the brightness versus the environment of the brightness, the outdoor environment. Or you could also sometimes put photochromic lens, which is get darker with the UV of the sun. But here is an example. If you'd like to use outside a display and you need a target for the brightness of the image over the brightness of the outdoor of only 2, and the display brightness of 700. So what people did is they put a kind of shading between the display. If it's shading of about 20%, it means you have the equivalent of 5,000. This is what Microsoft is doing, that ODG is doing. So on the right, you have an equation. It's a little bit to cheat with the brightness, but it's a way to deliver the right brightness without effort. Now, there's another issue, what we call the versions accommodation issue. What that means. The image position for the eye is very important, depending on the use case. For medical use case, sometimes the focus issue for the field of the surgical field, it's between 0.5 to 2 meters. For the industrial use case in factory, it's larger. It's about 2 to 4 meters. So if you don't adjust the focus, you have a discomfort, right? So here you have two situations. If you have monocular glasses, you have rivality between right and left eye. And then you have a discomfort if the focus is really very short, meaning less than 2 meters. If it's large enough, the depth of field help you to avoid this rivality. Here, what we call flip view, you could also have, like in our glasses, a system that flip up and down to allow people to have better situation. In binocular, the situation is worst. Why? Because even if you have the same data for right and left eye, the eye forced to focus at short distance and large distance. And the strain generated by this is larger than with the monocular. So normally the version accommodation issue should be solved by light field that I will talk later on. The other requirement that I see that's very important, of course, there is requirement for regulation. So in the United States, any glasses like my glasses or any HMD should follow the FDA regulation about the drop ball test. So what drop ball test is, you take a ball of metal ball, you drop it from 50 inch on the glasses or the light guide, and it shouldn't break. So today, if you consider all light guide based on glass, it never works. You have other requirement also on cost. It means the display cost should be low, mainly for large volume, and also its complexity and assembly should be affordable. You should have high manufacturing yield and scalability in production, which is not the case today for all the technology. So let's start by looking to the existing technology today. I start with this, what we call free air optics. For me, it's a residue of old classical optics. On the left, you have a scheme on the optical system. It's very simple. It's an assembly either of flat mirror at 45 degree, flat mirror with curved mirror. So these systems here, for example, used by ODG, are cumbersome, and there's a size issue, especially in front of the eye. They have low efficiency. Why? Because the light is crossing 2 times the optics, and they should maintain high transmission. This is why it's low efficient. There's low barrier entry for optics, but the main problem is subject to dust deposition and cleaning. So now we think the best technology today is based on light guide. So what the light guide? The light guide is, if you see all these systems, you have on the temple here the microdisplay. You collimate the light, and in front of your eye, the light guide guide the light and reflect it into the eye. There is actually 3 families today. I start from the left. You have what we call the diffractive technique. The presentation before explained one of them. How it works, actually, you have a microdisplay that collimates the light, and you have the light is diffracted, is encoupled inside the light guide, and outcoupled. So by diffractive technique, it either use holographic optical element or simple surface relief diffraction. So it has very high transmission ratio, up to 85%. It's very good. However, today, this technique need to have 3 light guide, 1 for each color. If you look for a HoloLens, they even have 4 light guide. So it's very complicated for the assembly and still limited in field of view, except for DigiLens technology, where they are using photopolymer, switchable, and with high modulation for the material. On the, you have a polarizing technique used by Lumos, which is a stack of several wafer, actually. Each wafer has a reflector. So this technology suffers from a problem of how to produce this kind of light guide, because sometimes you have to stack, to glue 6 wafer precisely, cut them, polish them, and assemble them. And on the right, you have what we call reflective technique. So starting from Google, where you have only 1 reflector, or Epson, also 1 reflector, and the technology used by Optinvent, where you have array of reflector, means these are mirror. They reflect all the light, so there is no color issue, where for the diffractive technique, you may have color issues. So anyway, we can say about all this technology, each technology is pushing to reduce the footprint, to have better performance, but the problem of cost and the performance still there. So some word about the Optinvent technology. This is the only technology based on mold plastic light guide. Actually, what you see in all these technology, the light guide sometimes is made by assembly of several components. Here, what's good with this technology, the light guide is mold, and you get it one in one, and you could produce a lot for low cost. Even the collimator, everything is in plastic. It has good performance also. And the transparency, you could adjust the transparency because it's a simple coating, a silver coating. Now about the other technology, or about the future, there's a new approach for light guide we call nanostructure light guide. So this technique works in air. It means the light coming in from the air, and when the light entering, you have a kind of nanostructure to diffract selective wavelength at selective angle to extract ray toward the pupil. And the other ray coming from the outside cross all the way and is not diffracted. So there is a lot of, it's a promising technology, but still really in R&D stage. It can generate also large field of view, but the main problem for this technology is how to generate large eyebox. Because if you only have to direct the light to only one point, it's very easy, but to get large eyebox, it's very difficult. And for the time being, still the color issue is mean you need to have 3 light guide, 1 for each color, to stick them together in order to generate color image. Now about the light field, I start by explaining what light field is. The light field is a way to, or today, when you wear any glasses today, when you see the virtual image, all the image is located in one plane, okay? You cannot really focus a different plane. So the light field idea, which is a very good idea, is to have a display that behaves exactly like the eye. The eye is moving all time, focusing at different distance. And here the idea is, if you see the human eye here, is to be able to focus one pixel A at distance D and one pixel B at different distance. So for that, you have really a lot of requirement. You need first to have high-speed image generation at pixel level. This is why if you have very high definition image, means you need a lot of computing for high resolution display. You need also different display. So sometimes you are using stack of different display or time sampling in order to focus a different distance. And if you see this focus distance, normally in order to have a display like the eye, you need different focus distance. And this focus distance, you need more focus distance when you are close to the eye. So you need, in that case, to have the ability to display, for example, at least 4 focus plane to have a realistic rendering, not 2, like other product now announcing. Why? Because, I mean, to have really smooth transition for the eye, 2 is not enough. This is why the optical system and the footprint and full computing platform should be integrated in very small size. And for me, for the moment, is not there for a consumer product. You have another requirement also for this system. You need to hide the information when displayed behind an opaque object. So this is something HoloLens is doing today, but this is also add a new difficulty. So for me, the principal challenge is, with this technique, is to make a minimum viable product with a small footprint and affordable cost, which we are not there. So as a future trend for optical technology, you can say that definitely the light guide technology is the best one. Why? Because for the footprint, all the electronic, the display is on the right, and only in front of the eye, you have, like your glasses, transparent glass. And so you could have also, for the field of view, you know, you could have larger value, but depending on the use case. It means if you are considering industrial application, you don't need large field of view. You need just information in front of the eye in industry. However, if you look for medical application, you need higher because you need binocular, you need to see some stereoscopic information. For game, you need the highest field of view because gamer would like to have larger field of view. And here is the opportunity, actually, that when you get a field of view larger than 60 degrees, it's a way to replace the VR by the ER, which is the main objective for ER. Now, for the rest, for the component today, the microdisplay, which is used to generate the image, you have different technique. Here, LCOS, which is liquid crystal on silicon, this is the technology that are most used today. I think it should be there for the next 5 years. Some other manufacturers are using DMD, like DigiLens. DMD is quite complicated because it's monosource, and sometimes it's expensive and complicated to implement. OLED technology could be very good because it has very good contrast. The problem is not generating today enough brightness to be used. You have the MEMS technology. It could be used too, but the problem when you use laser close to the eye, you have some issue with the laser beam quality cost and safety and mainly regulation. It's not easy to put laser into the eye today in a consumer product. You have another technology that's developed now, which is LED-based. It is not organic LED, is LED. It means like you have a matrix of LED, and this technology is able to deliver very, very high brightness, up to 1 million nits. There is a development in the United States and in Europe, and with this, you could really solve all the battery life, all the efficiency issue. For the light source today, since we are not using emitting source, you have white LED, almost used by all the manufacturer, which had the best ratio efficiency cost. RGB LED is very difficult because when you are using RGB LED with a sequential color, you have what we call color breakup. It means when you move your head, you see the color break. And bigger is the field of view, bigger is this phenomena, and you need to run the microdisplay at very, very high frequency. So there is also laser source. It could be alternative for high-end display or for head-up display, as my colleague showed you. When you need high brightness, very, very high brightness, above 10,000, sometimes laser is a good solution. So I hope to give you an overview about what we have today. Thank you for your attention.